I've always wanted to do that. That's better. Cheers. Let's build a house on a tree, shall we? We have a map of a forest which shows us the heights of each and every tree. Our job is to count down how many trees are visible from the outside of this map. Anything that is on the perimeter or on the border of that map will be visible. However, what we need to deal with is, for example, for this particular tree, we need to take a look at it from all of the possible sides, from the top, from the bottom, from left and right, and see if anything blocks the view. What we care about is, are the trees visible at all from at least one of those locations? It doesn't have to be visible from all four. That's what I'm trying to say. And as always, we pretty much get test cases for free. So let's use that. This is our example map. Here we have the test for the whole solution, which should count out as 21 trees visible from the outside. But we'll also take a look at smaller tests. First is confirming that the tree is on the edge, because as I mentioned, anything on the edge is straight up visible. We'll be looking at the tree at the position that is 1, 1. So this time around it will be 2, here also 2, and here we also are looking at 2. But we're looking from different directions, from the top left or the bottom, and we also expect different outcome judging or looking at the map as a general thing. This test is even more important, because this one targets once again a tree at 1, 1 position, however it's looking at all 4 directions right away. Let's go to the solution. First, from the string that is our input, we just read the trees. I've modeled the trees as a list of lists of integers, just because we are mostly interested in the heights of the trees, nothing really else. We're also remembering number of rows in the map and number of trees in each row. Next we run 2 for each loops, and we're looking at each tree separately. We try to decide whether the tree is at the edge of the map. If it is, it will be visible for sure. If it's not, we will run the function isVisibleByIndex. IsVisibleByIndex splits the logic into 4 parts as 4 directions from top, bottom, left and right. First we grab all the trees that precedes the tree we are looking at. Then we take a look at height of the current tree, and we're just making sure that all of the preceding trees are lower than the height of the current tree. Then the tree is visible from this direction. Bear in mind, get preceding trees is at this point a little bit more complicated than it should for this particular solution, but that's because part number 2 of the whole task influenced this particular function. Get preceding trees grabs the trees that precedes the current one. For the next part, it will be important that this list will be actually ordered from the tree we're looking at to the outside or to the edge of our map. And since once again we're interested only if the tree is visible from any direction, we pretty much go like this. If at all we have a true it is visible, it's already visible, so we don't have to even calculate for the rest of the directions. And that's it. That's the whole solution of part 1. Now part 2. We calculate a scenic score for each of the trees. We calculate that because we want to find the perfect tree to build our tree house for the elves. Scenic score, it's looking from this particular tree in once again all 4 directions and counting how many trees we can see. If we are looking from this tree to the left, then we count how many trees are shorter than our current one. The overall scenic score for each tree is just multiplying scenic score in each direction. In this very example, we're looking at the highlighted 5, and the scenic score is 1, 1, 2, 2. If you multiply it together, it comes out as 4. Then we take a look at a different example, a different 5 actually, and this time around the scenic score would be 2, 2, 1 and 2. Once again multiplied, it gives us 8. So what we are trying to find is the highest possible scenic score for the perfect tree with a perfect view. Looking at our tests, we know the outcome of the highest possible scenic score for our example was 8. That's what we are using. But we also got 2 particular examples for 2 different trees. For those 2 trees, we also got a scenic score from each direction. So we also test that to help us out while building our solution. Alright, let's take a look. The start of the logic is quite similar. We read from the input trees, then we run 2 for loops, and in the end we just calculate the scenic score for each tree. Scenic score is actually a multiplication of each of the scenic subscores from each direction, or rather looking in each direction, looking to the top, to the bottom, to the left and to the right. Once more we grab proceeding trees, however this time around that direction is important, because as soon as we hit a tree that is the same height as our tree, we stop counting. And once we build scenic scores for each and every tree, we just select the highest one. That's it. Let's see the output. Here you go. Thank you very much guys, I'm happy you've been here, I hope you had some fun. Trees that are visible in the first place, right? First we grab all the trees